Hi, last meeting is we've discussed about resistors in series and parallel connection. Note that there are circuits that can't be reduced by using simple series parallel combination. For example, this bridge circuit shown here. So there are several techniques in order for you to solve the current and the voltages across these resistors. And one of these techniques is called as Kirchhoff's rule. So basically, we'll be using some few or defining some few terms here. When we say junction, it's simply a point where three or more conductors meet. So here, point A is a junction, and even for your point B. Okay, there are three conductors connected. But point C and D are not junctions. They are simply wire nagiban. They are bended wires. Okay, another wire, bended wire here. So moving on to our Kirchhoff's junction rule, it states that the algebraic sum of the current into any junction is 0. So it means to say the current entering into the junction is simply equal to the current out of the junction. So no current stays into the junction. So it follows conservation of charge. A simple analogy for this one is the flow rate of water in a pipe. The water leaving the pipe is simply equal to the flow rate of water entering it. And we can also use some sign conventions. The current approaching the junction would be positive, and the current leaving the junction is negative. Or shall we say, we'll use another analogy for this one. So we'll have here, for example, I have here I1, for example, entering into the junction. And here's your I2 and I3 and I4. So all you have to do is current entering into the junction is simply equal to the current, the summation of current leaving out of the junction. Applying this junction rule, so you'll have here your I1, siya lang isa, entering into the junction, which is simply equal to I2 plus I3 plus I4. So the other one is what we call as Kirchhoff's loop rule, or sometimes called as KVL, or Kirchhoff's voltage law. So it states that the algebraic sum of the potential difference in any loop, including the associated with EMFs and those with resistive elements, must be equal to 0. So meaning to say, in a closed loop, the potential difference, the summation of all the potential difference in a battery or in a resistor, that is simply equal to 0. You must remember some sign conventions specifically for EMFs. You'll have a positive value for your EMF if the travel direction is from negative to positive nga potential, or if it's from lower to higher nga potential. And also you'll have a negative value for your EMF if it's from higher to lower nga EMF. So ang inyong timanan is asa mag-end ang battery. If sa positive, well, then it would be a positive nga value for your EMF. If sa negative, well, it would be a negative nga EMF. If it's a resistor ang loop nga agian, so ang tendency is that it's a positive nga IR. If the travel or ang loop is opposite to your current direction, it would be positive, and negative kung same og direction ang current ug ang loop nga directions.